Hi, my name is Jason Harlow. Welcome to my V Office Hour. I'd like to go over Physics 132 H1F Fall 2009 Test 2, Version 1, Question 8. This is about the magnetic field. It comes from Knight Chapter 33. And there's two parts to it. One is the magnetic field created by current through a straight wire, and another is the magnetic force on a moving charge in a magnetic field. So first, let's carefully read the question. An electric power line carries a steady current of 150 amperes toward the north. At a distance of 5 meters below the wire, a golf ball flies by traveling directly west. The golf ball has a net negative charge on it. What is the direction of the magnetic force on the ball due to the current in the wire? A north, B south, C up, D down, or E the wire produces zero magnetic force on the ball. So to go through a little background, page 1002, chapter 33 gives the right-hand rule for fields, which is you point your thumb in the direction of the current and you curl your fingers around the wire to indicate a circle. Your fingers point in the direction of the magnetic field lines around the wire. And then, if you go forward to page 1018 on magnetic force on a moving charge, that gives you another right-hand rule, which is for magnetic forces. You have your index finger pointing in the direction of a magnetic field and your thumb pointing in the direction of the velocity of a positive charge. Then your middle finger will point in the direction of the force on that charge. So we'll try to apply both of those rules to this problem. So let's take a look at the solutions. Okay, so we can take a look at my solution. First thing I've done is draw a diagram. And let's maybe try it from above. So here's northeast, west, northeast, southwest. The current is flowing towards the north and the velocity is towards the west. Now we're asked for the direction of the magnetic force on the ball. And that's going to be due to a magnetic field. And the magnetic field will be due to this current that's going through the wire. So there's actually two steps to this problem. Let's go through it carefully. Step 1 is that the wire produces a B field, and step 2 is that now you have to calculate the magnetic force on a moving charge in that B field. So step 1, we're going to use the right-hand rule for fields, which is just that your thumb points in the direction of the current, and then you bend your fingers, and that's the direction of the magnetic field going around that current. So in this case, we've got above the wire there should be magnetic field towards the east, and below the wire, which is where the golf ball is, it says 5 meters below the wire, so we're below there, the B field is towards the west. Step 2 is now that we know the B field is towards the west and we have a velocity towards the west, we would normally use the right-hand rule for forces, where you have magnetic field is in the direction of your index finger, the velocity is in the direction of your thumb, and the force is in the direction of your middle finger. But in this case, the velocity and the B field are actually in the same direction, so there's just zero force. If these are parallel, you have zero force. So, it's a bit of a trick question. The wire produces zero magnetic force and the ball is correct. Okay, so the main points here are just that, first of all, a current produces a magnetic field. If you have a straight wire, then there's circles of magnetic field going around that wire, or if you have a solenoid, then there's straight lines of magnetic field going down through the solenoid. The second point is that if you have a charge, or charged particle, moving, then if it's in a magnetic field, there will be a force on it. And this force is found from a cross product. It's F equals QV cross B. So you have a charge Q moving at a velocity V. You cross that with the B and you get a force on it. And you use that second right-hand rule to find that force. And with a cross product, if you have two vectors that are parallel, then you get 0 as your cross product. So in this question, the velocity and the magnetic field both turned out to be in the same direction, meaning that there's no magnetic force on the golf ball. My name's Jason Harlow, and I approve this message.